away.
Okay, let me just share my screen here. I hope that everybody, Ray, can you see the collage with the parts?
Yes, I can.
Okay, very good. Yeah, thanks everybody for joining. And as Ray mentioned, the newest division of the newest ultrasonic welding division for Herrmann Ultrasonics is welding of metals. And basically that is looking to capitalize on the trend that we all see in electric vehicles. So we've introduced equipment that borrows the heart of our system, the generators and converters, the very proven technology that we have in our generators and converters, and applying that to ultrasonic metal welding of the anodes and cathodes, the foils within a lithium-ion battery, or the battery management system, the high voltage cables that supply the motors and whatnot in an electric vehicle. As Ray said, that's kind of my job by day, and job by night is mentoring some of the newer salespeople, and then also traveling with them, viewing new applications, but then also doing things like this customer outreach, where hopefully we can give you some additional information to make your lives and your jobs a little bit easier. So this is the introductory class. This is a 1 hour segment of something that we typically do that lasts a full day. That class is typically either held in our headquarters in Bartlett or in one of our field office locations. We do have a lab in Lowell, Massachusetts with a machine there. So we've held this class there. The difference is that it's quite a bit more condensed, and it's divided up into 2 segments. So this segment is the basics class. So we'll be talking a little bit about the machine, a little bit about how the process works, what are some of the components, those kind of things. So let's jump right in, and I'll give you some definitions here. So basically, the ultrasonic plastic welding process is a joining method that uses the principles of acoustics to create frictional heat, producing a molecular bond between thermoplastic parts. So down at the polymer level, at the molecular level, what we're looking to do is excite those polymer chains, break those polymer chains as the material melts, and then have them relink and rebond together with the other part so that it's an imperceivable joint that is seen. And during this ultrasonic welding process, the mechanical vibrations are introduced into the parts utilizing amplitude, force, and time. And as Ray had pointed out earlier, if there's nothing else that you get out of this class, I would say that is really the fundamental building block that we should all be aware of. And the analogy that I use, it's like cooking or like baking a cake. There's a recipe, and within that recipe, there are temperatures and times that go into baking that cake. So amplitude can be analogous to heat, and time, of course, is how long do you bake the cake or how long do you weld the part. So these are knobs or levers that we pull on in order to adjust or modify the recipe that goes into baking that cake or welding those parts. And then the exact process parameters depend on the material and the geometry of the parts. Larger parts typically take longer to weld, and then depending on the material that's being welded, whether it's a amorphous or semi-crystalline material, or whether it's ABS or polypropylene, the type of and the amount of amplitude that's used is adjusted, again, based on those 3 levers or knobs of amplitude, force, and time. So sound is a pressure wave which can spread in elastic media such as gas, liquids, and solids. And these are the frequency bands in the range of acoustics. we use 3 different frequencies, 20 kilohertz, 30 kilohertz, and 35 kilohertz. But the normal human range ends at about 30, 32, 33 kilohertz. And people can say, yeah, but I can still hear some of the welding that's happening. And typically what's going on there is that the subharmonic resonance of the plastic part itself is what you're hearing, but the true 20, 30, or 35 kilohertz may be a little bit outside of normal human hearing. And as we age, the higher frequencies typically aren't as detectable as they once were when we were younger. But this slide also shows that the technology behind ultrasonics is used in a variety of different things. You know, anybody that has seen a sonogram of a child developing and his mother can relate to this. But you know, bats use ultrasound to kind of hunt and find their prey. So it happens in nature, it happens in industry. There's a lot of different uses for ultrasonics. There are basically 2 different ways of propagating the wave. It can either be a transverse wave or a longitudinal wave. An example of a transverse wave is if you drop a pebble into a pool or into a lake, you see the ripples kind of undulate up and down and spread out from the direction of propagation is perpendicular to the rock falling into the pool. A longitudinal wave, on the other hand, the direction of propagation and the direction of vibration coincide. And the example there is a sound wave. So when we create a longitudinal wave in the stack, the vibration is up and down. So the stack, as it's applied to your plastic parts, it acts as like a mini jackhammer. So it's not scrubbing the parts, and nobody can see me, but I'm rubbing my hands together. It's as if you were clapping your hands. So the effect that is produced is a bit of a micro jackhammer against those plastic parts. And as we've discussed, you know, sound waves are mechanical longitudinal waves, and we split them up into lambda or wavelengths. And as the frequency goes up, the wavelength of the sound traveling through titanium, which is our chosen material for the stack, as frequency goes up, length goes down. So 35 kilohertz tools are shorter by nature than 20 kilohertz tools are. So this micro jackhammering effect that we see, how big is it? So a human hair is about 100 microns in diameter, and the typical amplitude that we see, and what I'd like to point out here is that it's 0 to peak. So at rest to its maximum excursion, 0 to peak, we typically see something in the range of 30 microns. It can be as high as 50 microns, but again, we're talking about 1/3 to 1/2 the thickness of the human hair. So it's a very, very small amount of movement. The fact that it's vibrating 20,000 times or 30,000 or 35,000 times, very fast movements, but very small movements. So some additional definitions here. So again, amplitude is the 0 to peak excursion of the Sonotrode face while in expansion. So the Sonotrode contracts and expands, contracts and expands. So the amplitude that we're measuring is from 0 to peak. So that's amplitude. The definition of frequency is the number of cycles per unit of time. So every time that you see the wave or that you get that excursion of peak to peak, that is the definition of frequency. So 1 Hz or 1 hertz is 1 cycle per second. And in the case of 20 kilohertz, it's 20,000 cycles per second. Each of the components in the stack has what's known as a nodal point. the nodal points are here. So when it changes from that at rest to minimum excursion to the expansion and back to contraction, it has to go back through that 0 point. So if I were to hold a rubber band between my fingers, the two ends of the rubber band, and stretch it, you could hold the middle of the rubber band. That's the nodal point. So that's where we mount the stack, hold the booster, hold the converter, and at times, if we need to, hold the Sonotrode. At the nodal point is where there's zero movement, and so that's why we can hold and mount that tool within the actuator. So here's a graphical representation of the stack. So we have the converter, the booster, and the Sonotrode. The nodal points are here. And as you can see, when it goes through this expansion and contraction cycle, it switches back and forth, back and forth. In the case of 20 kilohertz, 20,000 times per second. And when the Sonotrode is in the expansion mode, the booster is in the contraction mode, and the converter is in the expansion mode. And you can see that each component changes state from expansion to contraction. And so the amplitude, although there is this peak to peak amplitude, in the contraction mode, it's somewhat theoretical. We don't measure that. We only measure Sonotrode amplitude from 0 to peak. So this is a pictorial representation of the cycle of welding. So we have our two parts. They are loaded into the fixture. The Sonotrode and stack and actuator move down. They make contact with the part. And typically there's a trigger force that you program based upon the size of the part. Once the parts are squeezed together or loaded up with force, and the trigger happens, we start to vibrate. And when we start to vibrate, this sacrificial bead, as we refer to it as the energy director, that begins to melt. The actuator continues to push with a pre-programmed weld force, and it pushes for some amount of time, some amount of distance, or some amount of energy and or power. That again is programmed. So you program in those parameters, and when that primary weld parameter is met, ultrasound turns off, and the welder switches to a hold time and a corresponding hold force, and this can be profiled as well. At that point, the plastic is still molten. We continue to press until the plastic cools, the weld in the joint cools, and then the Sonotrode moves up and you remove the welded part. So this is a video of a lure fitting, a typical application that we weld, and I just wanted to point out a few things before I start the video. So you can see that there's a gap here between the two parts. So the upper part, as we refer to it, is the driven part, and then the lower part, the part that's in the fixture, should remain motionless. The weld bead is approximately here in this area. So what you'll see is a full speed cycle. The Sonotrode will come down, load onto the parts, vibrate for a very short amount of time, 2 or 3/10 of a second. And then you'll see a wetting of the area here where the weld bead or the energy director or the shear, whichever sort of design is within that part, you'll see that melt, and you'll see it then bond and the Sonotrode retract. So there's a full speed video, and then there'll be a video at half speed as well. Oops, sorry about that. So again, the gap that you see between the parts gets smaller, and the wetting of the part, kind of the bond happens right across there. Okay, so there are various inputs and outputs into the machine. I've mentioned a few of them, but the main inputs that we have in the startup phase are we have to choose the frequency to use, and that's typically driven by the size of the part. Larger parts use lower frequency, smaller parts use higher frequency. And then we choose the amount of amplitude based upon the material that's being welded and the weld part design. When we move to the next phase of setup, we have to adjust and align the tooling, and we have to make sure that the parts are manufactured consistently. Part-to-part variations, cavity-to-cavity variations can affect the setup. And then our input parameters, input welding parameters, such as, are we going to weld by a collapse? Are we going to weld by an energy, an RPN? And then we weld the parts, and we get an output. Typically, there's either a graph, weld process data, and then we can do our quality control on the welded part, a pull test, a leak test, whatever it might be, to determine whether that part meets our requirements. If it doesn't, then we have to sort of go back to our setup or our input weld parameters and turn those knobs, make those adjustments, pull those levers to determine what is the exact recipe in order to get the best part possible. And we're aided by this data and by this graph, and we'll get into this a little bit later, but the graph has a joining velocity curve. And that's really our key guidance in our navigation system, if you will, that tells us what to do or what to adjust. We typically look for a linear joining velocity, and we adjust, again, the weld parameters in order to influence that joining velocity curve so that it is linear. Here's another video that I'd like to show quickly, but I want to just point out that this is using a high-speed camera that takes thousands of frames of 1,000 pictures per second. And here we have an energy director. So this is the driven part, and this is the stationary part, or the motionless part that's in the fixture. So what you'll see is, because it is so high in resolution and so zoomed in on the parts, you'll actually see this part vibrate. So as it's vibrating, you'll see the energy director melt, and the molten material will kind of flow. This is not an ideal weld joint design. There's no flash containment, so you'll see the flash kind of get stringy and start to flow out here. But I just wanted to show how the process looks at a microscopic level. So that energy director is essentially a sacrificial bead, as I call it. So it's molded into and designed into the plastic part, so that as the parts melt and collapse and come together, the final finished height of the part should be taken into consideration after the energy director is fully consumed. So it's important for us to get the right amount of heat into the plastic parts. So if we don't have enough heat, we may still melt the energy director, and the parts may stick, but there's really not a homogeneous weld. So initially, the crystallized solid part here, as you heat it up, those molecules start to move around, get excited, the polymer chains break, and if they cool, and we haven't reached the melting temperature of the materials again, you might get some sticking of the parts together, but there's not a true homogeneous mixing of the melt. When we have the proper amplitude or proper heat that we introduce into the parts, we get this intermixing or molecular exchange of molecules between the parts, and therefore we get a true homogeneous bond. So here's a close-up of what the screen looks like that we use for programming and for process control and for quality control. So on the graph, we can display various things as absolute distance, which is where the final point in space is after welding, RPN, or the amount of collapse that the parts went through, how much power was consumed, how much force was applied, what amplitude, what frequency, and most importantly, the velocity. So you can see here this blue line is the joining velocity curve, and this is almost ideal. I would maybe profile the force a little bit higher, because what's happening is that the energy director is a triangular shaped bead, and initially when it's at the point of the energy director, the melt initiation is pretty easy to achieve. But as you consume a larger cross-sectional area of that energy director, as shown in that previous video, typically more melt is consumed and we have to push harder. So you can see in the red curve here, we triggered at a point at about 80 pounds of force. We profiled up to about 100 pounds of force for the initial weld stage. And then you can see here, the weld profile increased slightly, and then it increased slightly again. So we have weld force 1, weld force 2, weld force 3. And again, this joining velocity curve is pretty good. I'd like to see at about this point, the curve continue on that upward trajectory. And therefore, what I would do is weld force 2 would have a little bit higher of a difference than weld force 1, and then potentially weld force 3 would have a higher application of force over weld force 2 as well. So that will influence the speed at which the parts are going together, which will result in this blue line being a little bit more linear. We also have some quality control things that we can look at statistically to see how in control the process is. Something that has to be taken into consideration is the volume of parts that you plan to produce. Is it a low volume application and maybe you can use a manual workstation? And you can see that the amount of time it takes to process parts on a manual workstation is quite a bit longer than if you were to have an automated system. So if you're making tens of thousands or hundreds of thousands or millions of parts per year, we typically will recommend a piece of automation be used for that application. We have some applications that in automation, the actuator is actually cam driven, and we've had cycles of up to 60 parts per minute. So again, depending on the volume of the parts that's intended to be produced in a given amount of time, day, month, year, whatever it might be, take into consideration whether or not you need a manual workstation or whether you need to automate that process. So now we'll get into the subsystems within the welder. So this is a picture of a benchtop machine. But whether it's a benchtop machine or whether it's an automated machine, the subsystems, the acoustical system, the mechanical system, the electrical system are pretty much the same. So in the acoustical subsystem, again, we have the stack, and I've been kind of concentrating on that because that's really the most important component. So the converter, as its name implies, it converts electrical energy into a mechanical vibration, and we'll get into the specifics there in just a little bit. The booster amplifies that mechanical vibration, and then the Sonotrode is custom to the application, and then that makes contact with the plastic parts. So the analogy that we like to use, it's kind of like the drivetrain in your car. The engine is the converter, just like the engine in your car takes air and fuel and spark and creates a torque or a rotational movement. The converter, again, takes electrical energy and converts it to a mechanical vibration. And then analogous to the transmission, the booster has different ratios or different gears, if you will, depending on the material that is chosen. So just like in your car, a specific gear is used for a specific speed. A booster or different ratio of boosters is used to amplify the mechanical vibrations. And then, you know, as the analogy finalizes, the tires, or where the rubber meets the road, the Sonotrode is custom and has to really grip the part and couple with the part. So theoretically, the part and the Sonotrode couple and they move together, and then the stationary part, the part that's in the fixture, remains motionless. So this graphical representation is using our finite element analysis, or our modeling. Obviously, it's greatly slowed down and it's greatly exaggerated, but you can see this longitudinal vibration. So the direction of propagation, the up and down, this micro jackhammering that we need is like you were to clap your hands together, not scrub your hands together. We can see the nodal points. And then we can see that in this case, we're measuring peak to peak, but the output of the converter is 10.5 microns, 21, 22 peak to peak. And then the booster, because of the nature of its design, above the nodal point, we have the driving mass, and below the nodal point, we have the driven mass. And you can see that there's a discrepancy. The driving mass is larger than the driven mass. And so therefore, more amplitude is created at the face than was inputted to the back. So from 22, we go to 55 microns. And it's not visible here, but if we were to turn the Sonotrode 90 degrees, you would see that, again, the driving mass above the nodal point is larger than the driven mass below the nodal point. So again, we have a gain ratio. So the amount of mass above is larger than the mass below. So therefore, we go from 55 microns of peak-to-peak input to 88 microns of output, or conversely, 44 microns of zero to peak. So again, here you see that the waves are small, increasingly larger, increasingly larger. So how does the converter generate this mechanical vibration? So it uses the piezoelectric effect, and basically the ceramic discs that are in the converters for converter stack, 20 kilohertz converter, 35 kilohertz converter, but they're essentially the same for piezoelectric ceramics here, with electrical leads coming in. So when we excite them electrically, they expand and contract, they vibrate mechanically. So as I mentioned, the booster, by nature of its mass above the nodal point and below the nodal point, creates what we call a gain ratio. So the input vibrations are typically smaller in the back and larger in the front. And each of the boosters has etched into it the ratio. So in this case, this booster, for 1 micron of input, outputs 2.5 microns. We do from time to time require a reduction in gain. So we see that we have reducing ratio boosters in both 20 and 35 kilohertz, but more often than not, more common is to see increasing gain. So in 20 kilohertz, we have ratios of 1 1/4, 1 1/2, 2, 2 1/2, and 3. In 35 kilohertz, we have ratios of 1 1/4, 1 1/2, 2, and 2 1/2. In setting up a process for our customers, we are essentially responsible for picking the right booster. The reason we're training or teaching about this is that sometime down the line, you may change your material or something else may change in the process. So how do you get the process back into control, or how do you get the output to meet your requirements? More often than not, it's a change in amplitude that will affect how the parts are welded. Another question that often comes up is about this mounting ring. Why is it there? How does it work? What's inside there? And a common misconception is that it's there to kind of bolt together the two halves of the booster. And this isn't true. The booster is one solid piece of titanium, but again, because if you think back to that rubber band analogy that I made, if you grab the two ends of the rubber band and stretch it, the middle of the rubber band can be grabbed and held because there's no motion there. So that we use that to our advantage. We further isolate the ability to hold that nodal point with this mounting ring, and then the stack is placed into the welder using that mounting ring location to hold the stack within the actuator. The components of the stack, the converter, the booster, and the Sonotrode, are held together with a stud. These studs are threaded pieces of titanium, and this is the stud for 30 and 35 kilohertz, and this is the stud for 20 kilohertz. So you can see that it's nothing more than, you know, a headless screw or a threaded rod. We place a stud between the converter and booster, and we place a stud between the booster and the Sonotrode. So there's two studs per stack, and once the stack is assembled, we have to torque those components together. And for 20 kilohertz, the torque spec is 74 foot-pounds, and you can see the other torque values here. But sometimes what happens if a customer disassembles the stack, or if they have to change applications and they remove the Sonotrode from the rest of the stack and put a different Sonotrode on, more often than not, what happens is they don't torque it high enough or well enough. These torque specs are relatively high. For those of you that might have some other machines, you may have experienced putting some sort of an anti-seize or a mylar washer in between those components. We manufacture our components to a higher flatness and surface specification, so therefore we don't apply any type of lubricant in between the stack components, and we don't place any sort of mylar washers in between. Clean, flat, dry, and torque to a higher specification. So as you can see here, there's a variety of different Sonotrodes. The Sonotrodes come in many different shapes, sizes, and materials. Here are just some round Sonotrodes, larger round Sonotrodes, some blade Sonotrodes or block Sonotrodes. And you'll notice that some of these have what we refer to as slots. So there's slots here, and the slots are used to channel that longitudinal vibration up and down, and not to stray or not to vibrate in a parasitic mode, as we call it. A 20 kilohertz Sonotrode is about 5 inches long. So when a Sonotrode becomes wider than it is long, the vibrations don't know whether they're supposed to be going up and down or at an angle or transverse. So these slots are added in very specific locations. They're very specific in their width, and they're very specific in the location from the back of the Sonotrode and the front of the Sonotrode. All this goes into the tuning aspect of the tool, because the tool has to vibrate very precisely at 20 kilohertz. So again, these slots are put into larger Sonotrodes that are wider than they are long. The different materials that we typically use are either titanium, aluminum, or steel. I would say about 75 to 80% of the tools that we make are made of titanium. And then the other, 10% in aluminum and 10% in steel, plus or minus. Titanium has the best mix of strength and elasticity. Aluminum is very soft, so it can have more amplitude or it can be stretched more than titanium. However, because it's softer, it can wear out faster as well. So on the other end of the equation is CPM steel. If you have a glass-filled nylon, for example, and we've seen applications of glass-filled nylon up to as much as 30% glass fill. The glass fill is abrasive, so the tool can wear. It's making contact with, the Sonotrode is making contact with that plastic part 20, 30, 35,000 times per second. So just as if you were to beat on something multiple times, it'll deform, it'll wear, it'll change. So we choose the material of the Sonotrode depending upon the material of the plastic part to be welded. And then furthermore, we can add coatings, such as a hard coat anodize on aluminum tools, tungsten carbide on titanium, chrome plating. We've used diamond coating, we've used nickel Teflon. There's a variety of different coatings that we can customize to apply to the face of the Sonotrode to minimize that wear or to affect the aesthetics so that blemishes are minimized on the plastic parts. And then furthermore, and not so common, is that we can add vacuum to a Sonotrode, or we can add a nodal mounted plunger. And these types of applications, if you had a component like a membrane or a filter or a valve, maybe something that has to be pushed out of the way of the parts welding prior to welding, these components are added to the Sonotrode to assist or help in that type of application. Each of the Sonotrodes that we manufacture has a label like this, laser etched into it. It has the Sonotrode serial number that uniquely identifies that tool. And when we manufacture a Sonotrode, every drawing, every quality control document is stored. And if you need a replacement, therefore we can make an identical replacement to be used if your tool does wear or breaks or something else were to happen to it. And I can't stress enough that because these tools are custom, having a spare in your facility is of utmost importance. It's really an insurance policy, because if the tool were to break or to wear, they do take several weeks for us to produce. If you can tolerate that amount of downtime, then maybe you don't need the insurance policy, but most customers we find can't really be down for more than a couple days. So having a spare is really very critical. The gain ratio of the Sonotrode is etched into it, the maximum booster that we suggest you use, and the weight is also etched into it. Typically, we try to match the gain of the booster and the gain of the Sonotrode. We try to evenly distribute that gain ratio, because you don't want one component to be stretched harder than the other. Gain and stress are directly linked. So the higher the gain, the higher the stress. The more you stretch the booster, the more you stretch the Sonotrode. It's like a spring. Eventually that spring doesn't go back to its natural state, and so the Sonotrodes will fail. They will eventually exceed their life expectancy. So therefore that goes back to why you should have a spare as well. And then just a small note on the weight, because we very precisely control and can calibrate the forces that are applied to the part, the machine knows the weight of the booster, the machine knows the weight of the converter, the moving mass weight of the carriage, all these sorts of things. but it doesn't know the weight of the Sonotrode. So this is an input. You input the weight of the Sonotrode so that when the machine calculates the forces that it's applying, it's able to correctly apply and very precisely apply that force. So something else that the finite element analysis helps us do is to eliminate those parasitic frequencies that I mentioned earlier. A Sonotrode will typically have 2, 3, 4 different frequencies that it wants to resonate at, and it's up to our tooling designers to pick the right frequency and to tune the Sonotrode so that it vibrates in this longitudinal mode. And as you can see, the amplitude across the face of the Sonotrode is very even, whereas this one that has been improperly designed or improperly built has varying amounts of amplitude. So there's no amplitude in the middle, and there's more amplitude at the sides. So we have to pick the right frequency, tune to that particular frequency so that the Sonotrode and the tool do not vibrate in this crazy side load mode. And we do that through our finite element analysis. Just a small point on fixturing as we're kind of wrapping up here. They're often overlooked, but are very important. The part that's in the fixture should be held motionless. We want that relative motion to be created between the parts. So if the part in the fixture is resonating or moving, and we're not creating that relative motion between the two parts, then energy is lost, and therefore it's not going into the plastic parts to be welded. You may feel heat at the face of the Sonotrode. You may even feel heat in the fixture. But typically we want the part within the fixture to be very rigidly held so that it does not move during the welding process. We make our fixtures out of aluminum, steel. There may be a decoupling plate that's added. We can also make some prototype fixtures out of cast resin, although this is not as common anymore. With the increasing ability to CNC mill fixtures, we can really make a cavity or very closely match the part with our CNC machining of hard fixtures, and we typically don't have to cast resin for fixtures any longer. This slide I'm going to just quickly skip over simply because it gets into a lot of math, and again, for the sake of time, the size of the air cylinder, the amount of air coming in, those sorts of things result in a force. And again, as I mentioned before, the amount of force applied can be very precise and can be calibrated within the machine, and the amount of weight of the tool is also a component that goes into the amount of force that's being applied. The other things we have to consider is the friction of the slide mechanism against the carriage. We have some low force machines that have very low friction guide rails. So again, depending on the size of your part, the amount of force that's applied is critical. So the kind of machine that's chosen and the force range that it operates in is something that we will help, or we will actually select and recommend to our customers. But I just wanted to point out that we have different cylinder ranges and different guide rail ranges that are specific to the size of your part. Here I'd like to just point out the rigidity of the column. So you can see that the column itself is cast and square. So in high force applications, when the Sonotrode or the stack, the carriage, comes down and applies force, think of it as a big C-frame or a C-clamp. So if you push down with high force, the natural tendency of the actuator would be to deflect. So take that into consideration if you have a large part or you need to apply higher forces, that the rigidity of the system and the lack of deflection is taken into consideration. I'll just skip over this real quick. And there is an encoder within the machine that very precisely measures distance. So if we have an energy director that is fractions of a millimeter, 0.2 of a millimeter, 0.3 of a millimeter, something like that. We have to very precisely measure the amount of collapse, and that's what the encoder does. And then our trigger point detection. So we typically will set a range, maximum and minimum, of where the welder should encounter the part. So if you have part variations or if the part is misloaded, the welder does not just blindly go through and start the weld. So the parts have to be properly loaded and properly found by the Sonotrode. So once the Sonotrode finds the top of the part, comes to rest, and it's within this trigger window, only at that point will the encoder be zeroed and the welding starts, and then it continues until your primary weld parameter is met, whether that's a collapse distance or whether it's an energy or whether it's a power, whatever it might be. But it all starts with this triggering algorithm that we have in finding the top of the part. So the generator is responsible for taking the electrical energy from the wall, amplifying it to a very high voltage, very high frequency, and then outputting it to the converter. If you find yourself in between boosters, or you have a very specific amplitude requirement, the generator has the ability to minutely adjust by 1 percentage point to lower the amplitude. So in these situations, if you're in between boosters, we typically recommend that you use the higher booster and then kind of choke or throttle back the amplitude within the generator. Converters output more amplitude depending on the power level of the generator. So for very large parts, higher wattage is required, but typically higher amplitude is required as well. So if you have very large parts, it's not uncommon for us to recommend or use a larger generator or power supply. The generator has a digital signal processor, which together with the resonance scan, we recommend that once the stack is placed within the machine that you conduct a scan, and therefore the generator will match the output frequency of the stack and then track it throughout the cycle, because as it's loaded onto the part, the frequency can shift a little bit. And then as it wears or as it heats up or as the conditions change over time, the generator will continue to match the frequency and adjust so that the tooling is operating at an optimal point. The way that we calculate amplitude, again, because the output at the face of the various components increases, we have to multiply the output of the converter by the booster, multiplied by the gain of the Sonotrode, and then multiplied by the percentage within the generator. So in this case, if we're using a 20 kilohertz generator with a 2 kilowatt power output, 10.5 microns, times the booster ratio of 1 to 2 and the Sonotrode gain ratio of 1 to 2, and the generator is set to 80% amplitude. So 10.6 times 2 for the booster times 2 for the Sonotrode times 0.8 for the generator, we have an amplitude output in this case of 33.9. I'm sorry, I'm kind of run through here, just looking at the clock. We're up against some time limits here, but these slides will be available to everybody, and if you have questions, we can go over them specifically as well. But finally, the controller is a very important user interface. Shows you the graph here, the output parameters or the data for each of the individual parts that were welded, and then also some histograms of the weld process over time. So really what's quite important is that we can visualize the process within this graph. And again, the blue line, the joining velocity curve. And here you can see that the force profile is a bit optimized. So the discrepancy between trigger force, weld force 1, and weld force 2, an increasing profile of force, influences that joining velocity. And as we apply more force, we also see that the power, the green line, also increases. So the harder you squeeze or the more you push on the parts, the more power that's also drawn from the generator. Okay, so that concludes the basics course. Ray, I guess if we have a few minutes here, maybe we will run over a little bit, but like to open it up to any questions that folks might have.
Yeah, as a matter of fact, kind of expanded on the last time that we've been doing this. We try to get a little bit better. Bosco, I want to let you know that I already conducted a bit of a survey on the presentation and the details with some feedback, and a good majority of them got back, and they're all 9s and 10s, man. You are it.
Great, thank you.
I do have a couple of questions that came through on the chat. The first one says, how is the variation in bonding strength from part to part using ultrasonics? And I didn't want to answer it because I think there might be some variables there that you might want to kind of refer to. So that's the question. Do you have an answer for that?
Sure. Yeah, so the variability of the welding process is directly tied to the consistency of the molded parts. So ideally, if you have a single cavity mold for part A and a single cavity mold for part B, then the consistency should be 100%. It should be the same from weld to weld. If you have a multi-cavity mold, or if there is variability in the molding process, that will typically be seen within the weld process. And we do have tools at our discretion that we can choose the right process parameter. It might be energy, it might be distance, but oftentimes we choose distance as our primary weld parameter, and that's driven by the height of the energy director. So as long as the height of the energy director stays the same, the welder will adjust the amount of power and the amount of time that goes into the weld to accommodate those variables that you might see in molding.
Mm-hmm. Okay, thank you. Next question is, would ultrasonic welding maybe have less particles being generated than, say, spin welding?
In general, yes. In the afternoon class, we'll talk about joint design, and particulate generation or containment of particulate is directly tied to having a very robust design, a joint design. So we want to contain that flash. Spin welding in particular is a little bit more of a violent process, I'll say. So yes, there would be more particulate created in spin welding than you would see in ultrasonic welding. But in general, the amount of particulate that's created and lost, if you will, or that you can see, is directly tied to joint design.
Okay. And there is a question coming through for quality. By the way, the person who asked that question, Matt, said thank you. That sounds like a really great answer. And then there's a question around quality. I don't know if it's a specific or a more general question. So, but I guess I would say it sounds like there might be some questions around both the quality and strength, which you may have hit on, as well as the aesthetics and maybe how we address those.
Yeah, so from a quality perspective, we monitor all the data, and we can adjust or create upper and lower control limits that if the result of the energy, for example, exceeded the window for maximum energy drawn, then we can flag that part. So we can absolutely show that part A was within the weld process parameters and maybe part B exceeded the weld process parameters. So that one will be flagged as a suspect part. Most of the time you can't do 100% inspection. So a lot of our customers rely on the data that's output by the welder to create a quality plan for their parts.
So Bosco, I partially heard that. Did you say that our system does have some capability to reject a part if it doesn't meet one of the key parameters that we measure?
Yes, that's right. So over time and over gathering data and doing testing during the development phase, you should be able to quantify how much energy and how much power, how much weld collapse, those sorts of things are needed for a good part. So if the process, if your molding process creates variations in the molded part, then of course naturally you would see some variation in the welding process. The welder doesn't always create good parts out of bad parts, but if the part coming in were dimensionally different and it required more energy or less power or whatever it might be to finish the weld, that part will be flagged, and then therefore you can either scrap it or you can test it to make sure that it's still within the quality parameters. But yes, there is the ability to get data and quantify each weld.
Okay. Well, that seems to be it for the questions. I want to thank everybody who participated. Oh, okay, hold on. Last second.
Yeah, I see there's a question about Sonotrode failure. So as I mentioned, we suggest that there's a resonance scan done. So the generator and the stack match their frequency. So it's a good practice to periodically repeat that resonance scan, and if the frequency of the the frequency of the Sonotrode changes, then the generator, after additional resonance scans, will track that frequency. But at some point, and this should hopefully be years and hundreds of thousands or millions of parts down the line, if you see that resonance scan is not completed satisfactorily, or that under test conditions the power draw or the frequency is changing significantly, then it's probably time to replace the Sonotrode. There are instances, although very rare, that a Sonotrode can catastrophically fail, that it can just crack, and then therefore in those cases, then if the Sonotrode can't vibrate or it can't start, then you'll see zero power being drawn from the generator, or you'll see very low output numbers, and that's an indication that the Sonotrode needs to be replaced.
Okay. The quality question did come through. I think you sort of hit on it, but I'll read it just in case you think there's any nuance. But in terms of quality of weld, is there a feature that provides feedback to the uniformity of the weld? For example, if a part is offset, will the machine recognize that the weld may not be uniform?
In general, yes. Each application is different, but if you did have a misloaded part, or the part was offset somehow, the trigger algorithm will detect that the parts were misloaded, so the parts won't even get welded at that point. But if it was still within the trigger window and it did go through the weld, if the part is offset from the Sonotrode, then what I would expect is that typically the weld time would be very short. So if we expected to weld, let's say 3 linear inches, and only 2 linear inches got welded because the part was offset, then that weld would happen very quickly with less time and with less power. And if you have upper and lower control limits set around power, energy, or time, the result of that offset part will be lower weld times, lower weld power, lower weld energy, and then yes, that part will be captured as a suspect or bad part.
Perfect. Okay, so I'll let the team know that we do have another session this afternoon at 1 o'clock. Some, if not all of you, are participating, and so we'll see you at 1 o'clock. Vasco, thank you very much. I think this was extremely successful, and I'll have this as a recording. And for the folks, I am sending the slides along to you, so no worries about that. You'll receive them shortly. Thank you, everyone.
Thank you, everyone.
All right. Bye-bye.